Alright, so I've been working on this video. I'm pretty excited about it. It's going to be an overview to programming, and that's kind of really wide open. Um, Basically, what I want to talk about though, so my experience with programming from my history is a little bit unique, and so it kind of causes me to think about programming in a certain way, and it made this very interesting for me, this topic. So just really briefly, we had computers when I was a little kid, which back then was very uncommon, I think. But my dad was very into computers, so when I wanted to play a game on a computer, it was on DOS. So I had to type in commands just to open a program. So um, typing in some of those old DOS commands is a little bit similar to typing in, say, a line of code, for example. And later, I took C++ in high school, and it was very, I can't remember how it was taught, but from my memory of it, I don't think we got into object-oriented programming. I think it was more of a procedural focus. And beyond that, I've done programming with like robots, and um, I've done circuit design, both for electrical circuit design classes as well as like hydraulic circuit design classes. And so for me, I think about things very procedurally, very linearly, and I really like to think about things at a low level. But in modern times, people use high-level languages mostly, and the thought process and the algorithms and the way that code is approached is different. And I've done some of that as well. And so I kind of wanted to spend some time thinking about the relationship between those two. And my final, yeah, so that's kind of where this is going to go. Um, So this was what I originally intended to do. I cut some of this out just to make it a shorter video, but in the first part, and basically the way this is set up here, you can see visually, we're going from, high level to low level. And some of the things are not really programming at all. Some of them are technically not programming, but are pretty close, and some of them are programming. But all of them have in common that it's about algorithm production. And so going from top down, we have, so I got my handy dandy little pen here. See if it works now. And so we have the fit. No, it doesn't. I don't understand why it does that. Sometimes it works and sometimes it doesn't. It's because it's my, I can't figure that out. It doesn't like my tablet. All right, so we have physics theory on the top here, where I'm going to lay the foundation in physics for the program that I want to write. And I'm going to try to write the same language in higher level and lower, the same uh, program, same to solve the same problem in higher languages down to lower level languages based off this physics theory. Then a general flow chart that will work more or less in most of the higher level languages, and then not so much in the lower level languages. It would be a different flow chart, but just kind of to give just a general flow chart for how the problem could be solved. And then I'm going to talk about some programming languages here. So first, what I'm going to call an ultra high level programming language, meaning is not technically a programming language, but would just be doing functions in Excel. And it's very similar in the same way that entering in commands in DOS is similar to programming, but it's just not quite the same, but it's really close. It's definitely still using an algorithm to solve a problem. And so anyway, so that's here. Then Python, then C Sharp, which I'm actually going to skip. Then C++, assembly I'm also going to skip. STL, ladder logic I'm also going to skip, and circuit design, which I'm calling ultra low level because once again, it's technically not a programming language, but I think that the similarities are profound, and there are some key differences as well. And so see if I want to say any more here. So one thing, while I still have like all these languages up as a whole, is that there are uh, when you program with a language, it's not just about like the code that you're writing, it's also about the environment that you're coding in. And so that becomes true more and more as you go up the ladder of being higher level language, being more abstract. Because what happens is like when you program in Excel, you can do more in Excel, but the way I'm thinking of it is just the very basic Excel usage where you just enter functions into a cell. So in that case, anything to do with memory or anything like that is already being done by the general framework that you're coding in. And all you're doing is entering some various functions, and then when you do uh, connect different pieces together, sometimes the connections, you say you're not going to be entering a memory address, for example. You're going to be pointing to either another location within the framework, uh, that type of thing. Um, Python, I'm actually not familiar with the frameworks for Python. I haven't had to use them, and framework probably isn't exactly the right word. Environment, or I can't think of the right word, but um, so what I'm going to do is just a console project for that. C#, what I wanted to include, but for time's sake I left it out. I have done scripting in Unity game engine, and there it becomes very apparent that what you're coding in is the environment. So when you declare variables, when you reference different pieces of the code, the process is a lot different than you're just straight out typing text. And in C# in Unity, when you program with C# in Unity, sometimes your variable declaration isn't typing in a declaration. It's physically dragging and dropping something into a field that you created, for example. So that's what I wanted to include from that. But anyway, so you get the verbal explanation. For C++, I'm also doing a console project, and for the others, we'll get there when we get there. Yeah, so the problem that I want to solve, here's a bunch of physics theory. If you want to pause it and look over it, you can, but basically the basic idea is if we have a building and either we're dropping this out of a window or off the top of the building, I'll probably mix it up between those two as I describe the problem. We're dropping it from some fixed height, and we want to use that to calculate g. And what we want to do is, so due to the magic of calculus, we come to this equation that g equals 2 times the height that we dropped it from divided by time squared, the time that it took to fall squared. So we're going to use that to come up with an experimental value for g. And the only other thing that we're going to add to this is, let's say that we think that we can get pretty precise with our measurement of the height in meters, but the measurement of time in seconds, we feel like we probably can't get as precise as we need to. So we're going to imagine dropping the ball 3 times, measuring the time that it takes to fall 3 times, and then averaging that value. And we're going to use that average value here. So that's the basic setup for the problem. Here's just a general, very generic flowchart that I will most of the time follow in the code for solving the problem. So first we're going to want to print instructions to the user. We're going to request that the user enters a value for the height. We're going to input instructions to get the time and request that, and we're going to keep count of how many values we have. If we do not have 3 values yet, we're going to come up here and repeat and ask again. If we do have 3 values, we're going to do our math, and then we're going to output our result at the end. Pretty simple. All right, so the first programming language that I want to cover, I think I've already made the point clear enough, it's technically not a programming language, but is using spreadsheet. Here I'm using what is it called? The LibreOffice Calc. I'm used to Excel, so I may say that on accident sometimes, but pretty basic. You just enter in the values, in a cell, and then it outputs the result. And the formula that I use is right here, and basically it's literally just the math for the that we got from our physics equation, and it automatically outputs the value. So this is an algorithm for solving the problem using this environment, and it's here would be the part that's akin to programming, is creating this formula. Pretty basic, ultra high level. So Python, and I did Python and C++. I did them twice, both because I wanted to show them in a very procedural way, and next I also wanted to show them in a way that represents more what they would typically look like by a programmer. So we'll skip over this one and go to the next one, which is more of what it would end up looking like. So the difference is here I used a function that I created, and then I used a for loop, and that's going to become relevant because if I go back to the hierarchy real quick, so if you start at the top here of this like ladder, if you try to go down, if you create some code, well, this one really doesn't count. You're not actually writing code here. So let's start at Excel downwards. If you create some code at this higher level, and then you want to create the same code at the lower level, it's not always going to be possible without basically reconstructing the foundations that you're missing from the higher level languages. Meaning that you basically would almost have to remake Python to remake the things that you're missing in Python in order to do the Python code in some really low level language, right? But for the most part, any algorithm that works down at these really low level languages, if you want to just take that same algorithm and copy it up to a higher level, typically it works. I mean, not just copy and paste, but not copy and paste the text itself, but copy and paste the algorithm, which you don't literally copy and paste, obviously, but just reuse the same procedure and steps to solve the problem. You can typically go up, but not down. And so the question then about these higher level languages is what things that you're making use of that don't exist in the lower level languages. And that's what I wanted to say to get back to this. So here I'm using functions and for loops, which do not exist at the very bottom levels. And so, yeah, so basically, how does this work here? We create a variable g, set it equal to 0, and initially, and it that's just going to set aside some memory. And what memory it chooses is some interplay. It's either one or the other, or an interplay between the two of the Python interpreter and the operating system. I'm not actually sure which one of those, but the user, the programmer doesn't even have really control, not in a normal situation, of which piece of memory in the computer gets used. Next we're going to print out instructions to the user. We're going to print out some more instructions, and then also receive in whatever the user types and set it to an integer, and then put it in this other memory location, which is h, which again, it determines where that is, but what it's doing is reserving a chunk of memory for that value. We're going to print out some more instructions. Then we're going to go to this function that I created. That the function is going to calculate average time. And first thing we're going to do is create another variable called sometime set it equal to 0. We're going to do this for loop that's going to loop through 3 times. Three times, and ask for the time that the object took to fall. And then when it gets all 3 of those, it's going to divide that by 3 to figure out the actual average, add them together, and then divide by 3. Then what it's going to return is the average time value. And then when we have the average time value, this was creating the function. When we actually call the function down here is where it actually does all the stuff that I said above. And when it finishes doing that stuff, it's going to store it in this memory location. And then once we have that, it's going to take that and put it in here and perform this math. And the numerical result of this math will get stored in G. And then that value gets output to the user. And to demonstrate that, I have one of these here. Where's it at? Oh, I don't have this one open yet, actually. So the one that we're doing, I think, is this Python 2, although they both give the same result, just as I showed. One of those is the like procedural way of doing it, whereas one uses functions. Yeah, so here's the code that we just looked at. Actually, this is not the code that we just looked at. This is the other code that we did not look at, but it does the same thing. And when I hit, try to remember how to do this one. Run Python. All right, so now it pops down here. It's running the code in this like little console window. So 20, 3, 2, 1. So I don't think I said this yet, but to keep our testing the same, we're going to use 20 as the height of the window, 3 is the value of the first time, 2 seconds is the value of the second time, 1 second is the value of the third time, and I intentionally chose those numbers so that we can use integer values. So I'm going to use integers instead of what you would really want to use if you were actually writing this code to solve the problem. But I'm actually writing this code to demonstrate the comparison between the higher level languages and the lower level languages. And in the lower level language, it is much easier for me to it's much easier for me to just use integer values. So that's why I chose to use integer values here. And that's why I chose these numbers, which are a little bit crazy. 3, 2, and 1, those are really different, but it makes the math work out nicely so that everything can remain integer. And our experimental value for the gravitational constant is 10, which is pretty close to 9.8. All right, so there is Python. C++, so the main difference here, so Python does some of the setup stuff for you when it comes to this type of program that we're making. So the main difference with C++ is it requires us to, you could have, well, to be honest, I'm not as familiar with Python, but I'm pretty sure that you can have these kind of things in Python, whether it's technically if I remember the term right, this is a header, and whether it's technically a header in Python or not, I'm not sure, but I'm sure that you can reference libraries and stuff like that. Basically, what this is telling you that there's a and you know what, let's actually look at the next C++ one, because this is the procedural one. We'll stick with the one that's more. This is more of what the code would normally look like. Actually, we'll look at the procedural one, because you'll notice this is basically the same as it was in Python. We have a for loop. I think the only difference is I chose not to create a function here. But the namespace part is a little different. So the only thing that I did here was I did using namespace std up here, so I didn't have to enter it on every line. But if we go back over here, so we have this header, and this is telling us that we want to use IOStream. And inside of IOStream, there's a whole bunch of predefined code that we could use. And the one that we want to use is this cout cin. And cout cin is inside of a namespace that's inside of this header. And that namespace is called std, which you could put at the top like I did here, or you could put on every line by line as I did here. And so then what we have is, the next thing that we have is this int main, and this is always required in C++, and this is how this serves as the backbone for your program. And what it does is the code, I'll say it the way that it was told to me. I feel like this is a little bit ambiguous though, but basically the logic part of the code starts here and it ends here. And anywhere it needs to jump in between, it jumps from here to something and then jumps back to here. So that's kind of what's going on. And interestingly enough, later I'm going to talk about STL, which is used for in step 7 for Siemens PLCs. And there they use organizational block 1 is what they call it, but it's basically the exact same concept. The program logic starts there and ends there, and anywhere else it jumps, it jumps from there and then jumps back. And they do the same thing for Allen Bradley PLCs. They use main routine. So it's a pretty common thing, but in Python, so the higher up you go, they try to get rid of some of the extra fluff. So you'll notice there is none of that here. In Python, it's not necessary. The next thing that I did here, this is just generally considered good practice, is I declared all the variables up here. So these are all the memory locations that I want to set aside for the different things that we're going to input. And once again, just like with Python, I don't have any control. I don't know if you can technically, there's a way to have control, but the normal way of doing it, you don't have control of where these are represented physically in the hardware. And I think you wouldn't anyway, because I'm pretty sure that on a standard PC, the operating system takes care of all that so that you couldn't do it. But anyway, that's kind of a little bit in a direction I don't want to go. But I'm trying to say that there's a certain amount of control that you don't have. You do say that set aside this memory, but it decides where the memory goes. And the next thing then is the program here. You can see this is the procedural version. I just have it ask the user for the drop height. I store that value in the memory location I set aside. The same thing for each of the times. And then we do the math. First we do the average, then we did put the average value into the more fuller formula, and then we print out the result to the user. And C++ requires you to include this here. I'm pretty sure you can actually leave it out, but it's supposed to be there anyway. So yeah, so you'll notice that as we go down deeper, there's more extra stuff that seems like, why would that be there? Yeah, that's enough. So next thing I want to look at here, we did C++. I can run the C++ program. So here's it, and I'm using Visual Studios, and this is a console program, as I mentioned. So when I hit play, it's going to open up the console, and it asks me, what's the height? I say 20. What's the time 1, 3, next time 2, next time 1, and it prints out the result right here of 10. Yep, so there's that. Nope. Oh, where did it go? There it is. Okay. Now the next one, STL. And so this one's going to take a little bit more time actually, because now we're dropping down farther. And I wanted to include assembly because that's going to be more relevant to the PC world, which is kind of what we're focused on. But I have quite a bit of experience with programming with PLCs, and I have not done assembly programming. I've seen it, and I know that they're very similar, what assembly and STL. So just assume that it's similar, because it is similar. There's important differences, but when you compare it to the other things that we're going to look at, it's more similar than it is different, if that makes sense. So yeah. So, and I wrote this one on here twice, but this time the code is exactly the same. But this here has comments, and most of what you see on the screen is actually my comments. The code is actually very skeleton looking, and it's also very nonsensical. If you don't know anything about STL, this looks like gibberish. And so we're going to go through this line by line and see what's going on. And you'll see that the logic starts here. Everything above it is comments. And the key thing to know here is that this, so I can, I guess, take a step back. So a PLC, programmable logic controller, is a microcontroller. It's a specialized computer used in an industry to control machines. And so that's what this is, and that's what this programming would be used for. So in assembly, I believe they use memory registers, if I'm remembering correctly. But in Siemens PLCs, they use accumulators. So, well, actually, I shouldn't say that. That's not probably not the proper comparison. The places where the memory will be stored will be these memory words. And these memory words, MW, represents actual locations of memory, physical locations of memory on the hardware. And then we have these two accumulators, ACC1 and ACC2, and they serve as like working short-term memory. Yeah, so what we're going to do is we're going to go through this and see what happens. And the key is you have to track accumulator 1 and actually, yeah, we'll just do it there. Accumulator 2. And then we'll track the outputs too as we go. So the first thing that we do is this says to load 20 into accumulator 1. The next step says to transfer what's in accumulator 1 to memory word 100. So memory word 100. Sorry for my writing. I don't know why it won't let me use my tablet. Is 20. Memory word 100 is 20. Next, we're going to load 1 into accumulator 1. So this is a 1. It moves the 20 into accumulator 2. Then I'm going to transfer that into memory word 100. So memory word 110. 110 equals 1. Then I'm going to load 2 and transfer that into memory word 120. It's 2, and for reference, that's up here. 120 is the second time value, 110 was the first time value. Now we need to get the third time value, so first we have to load 3, because that's our measured time. This is going to be, no. Yes. And so then this moves the 2 over to here. Transfer that to memory word 130. Memory word 133. And now we're going to start the process of calculating average time values. So we're going to load whatever's in memory word 110. That's 1. So we're going to load 1. It moves 3 over to here. Now we're going to load what's in 120, which is 2. We're going to add them as integer values. So this is 3. The 1 stays there. Now we're going to load memory word 130, which is 3. So we have 3 here. Moves the original 3 over to here. Now we're going to add those as integer values. So we have 6 here. So 3 stays here. Did I do the load 3? I did not. Load 3 moves the 6 over to here. Divide as integer. It divides ACC2, which is 6, by ACC1, which is 3. So the result is 2. The 6 stays here. Now we're going to transfer what's in accumulator 1 into MW150. So MW150 is 2, and MW150 is the average time. So we just calculated the average time. Now we want to start the rest of the math. So we're going to load 2. This is 2, this is 2. We're going to load memory word 100, which is 20. So we have 20, we have 2. Well, that makes your hand tired clicking with a mouse all like that. Then we're going to multiply them as integer values. So we have, continue it right think this will be enough space. We have 40, we have 2. Then we're going to transfer this into 160. So MW 160 is 40. Where did I leave off? I did that one, I did that one. We transferred to 160. We're going to load the 150 value, and you'll notice I load it twice. It's 2, so we load 2, it moves the 40 over to here. Then we load 2 again. I'll do it the right way. 40, we load 2 again, it moves this 2 over to here. Then we're going to multiply them as integers. So this becomes the result, which is 4, and then this 2 just stays here. And then you guessed it, we're going to transfer it into a new memory location. So MW170, W170 becomes 4, which is the result of t, so the average time value squared. Then we're going to load the 160 value, which was 40. We're going to load the 170 value, which we just had, which was 4. So this was a 4. When we load 4, this becomes a 4, this becomes a 40. And then we're going to divide. It divides 2 by 1, which is going to give us 10. This stays a 40. And then this is our result. And we're going to move that result into memory word 200. Memory word 200 is 40. Okay, so that is how this program would operate in Siemens Sub 7, which I didn't use because I don't have a license for it to do it on here. But so that's how the program would run. And then basically what you could do is you could, just like with the higher level languages where you need to interact with the environment, here you could interact with the environment, or often you would interact with hardware, which would be an HMI, the device on the machine where people push buttons and stuff. So maybe, I don't think I actually set up the memory right in the beginning, but ideally someone could map these buttons to these memory addresses so that when they enter in the numerical value into the memory address, it goes into there, and then when this is ready to read it, that's where it gets these initial starting values from that it used. And then when it's done, it could output to this memory address, which then maps to the output visual display for the user. So that's kind of how this works and how this works at this lower level. And you'll see it has a very different feel than what we saw at these higher level languages. And the next one that I want to go over, which is the last one, which is actually my main reason for making this video, but I have to, due to the fact that it's actually really big and complicated even just to do this simple little math problem, which, our math problem, once again, going back to the beginning here, when we did it in Excel, all of the actual work is one line. When we did it in Python, again, you could write this in much less lines of code if you really wanted to. And so, and even in the other ones, it's a little bit, you see as you go down the layers of abstraction, it gets a little bit longer every time. Each one of these is longer than the one before. But by the time you get down to this level of circuit design, it's really, really huge. And so what I'm going to do is try to explain the parts and pieces, and you're going to have to use your imagination to fill out the whole picture. So basically, I think I have 3 slides here for this. Yeah. So here is the algorithm that I have thought of to use to solve the exact same problem. It's a physics problem, and we're doing the same idea where we input 4 inputs and we receive 1 output that is the solution. The main difference here is we have to input the numbers in binary, and we get the output in binary. That's just how I chose to leave it. And if I were to actually build this, and so the way that I want you to think of it is that we're using very small electronic components. So you're going to be using wires and transistors. And then in order to actually make it work in the real world, you're probably going to have to throw in some resistors, and you obviously have to have a power supply and some other things. But as far as like the control part of it, we want to think of it as just resistors, just transistors. And so yeah, here is the kind of the big picture algorithm of what would happen in the program. So we have these 4 values that we have to input. Once again, the height, time 1, time 2, time 3. The height is going to be 20, which in binary is 0, 1, 0, 0, 1, 1. The time 1 is 3. Binary is 0, 0, 0, 0, 1, 1, and so on. You can see there. So over here on the left-hand side would represent us entering in the values, and on the right-hand side is the output at the end. Now, one really interesting difference here is that in all the previous steps, the logic happens sequentially, and the output is waits for the previous steps before it happens. In this design, that doesn't happen. The output is constantly being updated by the changes to the input. So you would actually have to kind of wait to look at the output until you're done setting all of the inputs, if that makes sense, because it will be outputting the whole time, but you don't care what it says until all of the inputs are correct. So that's an interesting difference. And basically here's all of the parts and pieces that you would need, and how they're like wired together. So on the left hand side, as I said, here's our inputs. We input this height value into a circuit that multiplies these two binary numbers together. The one being the height value, which is the binary for 20, and the other being the binary for 2. Going back to our physics equation, that represents 2. So yeah, our physics equation was the magnitude of the absolute value of g equals 2 times h over the average value for time squared. So this represents 2 times h. And we're going to take that and send that straight to this other circuit, but we're not worried about that circuit yet. Let's move down here to the bottom. So we have this circuit to sum the 2 time values, again in binary, and it receives those both as inputs, and then it outputs the sum. Then this circuit's going to sum the result of this first addition circuit with times 3, and it's going to output that into a third circuit that divides the result of all 3 time values added together by 3. And it's going to take and put that in here. And then simultaneously we have another circuit that this is just a copy of the circuit above it that does the same thing and inputs that. And so what we're going to input into this circuit is the average value twice. And then this circuit is going to multiply those 2 average values. So working out with the numbers that we had, this would end up, we're going to take 1 plus 2 plus 3, which is 6, divided by 3, which is 2. And so we're inputting 2 into here and into here, which is 0, 0, 0, 0, 1, 0 in 6-bit binary. So this is going to be, this represents t squared, basically. And this represents 2h. And we're going to end up inputting both of these into this last circuit that divides 2h divided by t squared and outputs the result. Okay, so that's the overview of what happens. And digging down just a little bit, like I said, I'm not going to show every part and piece, but just give enough to give the sense of what it would look like to do the full project. Here is so this was like the outer big picture. Now I jumped all the way to the bottom to the nitty-gritty details, and then I'm going to go back to like the middle level. So what we have here at the bottom level, we want to think about transistors. And we're going to form transistors in two different ways. Well, three different ways, but one of them I didn't draw. Again, just trying to simplify things a little bit. This one looks a little more complicated, so I just didn't put it on here. But we have these three different ways of combining resistors, right? The one is an AND gate. So if if input 1 is a 0, input 2 is a 0, output is a 0. If either of them is a 1, but the other one is a 0, the output is still a 0. They both have to be 1s for the output to be a 1. An OR gate means that if both of these are 0, the output is a 0. If either of the inputs is a 1, but the other one is a 0, then the output is a 1, because it only needs to see at least one number 1 down here. And if both inputs are a 1, the output is also a 1. The exclusive OR, the functionality of it is very similar, except if both of the inputs are a 1, the output is a 0. It wants to see 1, 1, and 1, 0. It doesn't care which side is 1 and which side is 0, but it wants to see 1, 1, and 1, 0. This is a real quick rundown of the circuitry that we would use with transistors. Now, building transistors, so each of these here is built up of quite a number of transistors. And so this is called a half adder, which is this right here. So this is built out of two half adders and one OR gate. The half adder is built out of one XOR gate and one AND gate. And what the half adder says is, so we have this 2-bit number. So this would be B1, B0. And our options there are 0, 0, which is the number 0, 0, 1, which is the number 1, 1, 0, which is the number 2, and 1, 1, which is the number 3. And so what this is telling us, the half adder, is that if we have, this is exclusive OR. So this means if either of these is a 1, but the other one is a 0, then we put our result becomes a 1. And that's represented here and here. So that means if you're adding together two bits, 0 plus 1, or 1 plus 0, then you want this, which you imagine this turned on its side. So this would be R, and this would be C. So the bits added together, if you add, I should have drew these ones vertically, but anyway, if you add the bit 0 plus the bit 1, you're going to have a 1 in the R place, because this is the answer. And the same is true here. Now if you add two bits that are both 0, then well, we're not going to set off either of these. And so both the outputs are 0. And if you add two 1s, then the R place actually needs to be 0. And the next place over, which we're calling carry, needs to be a 1. And that's represented here because this is exclusive OR. So if both of these are a 1, this actually outputs a 0. This is an AND, meaning if both of these are 1, this actually puts out a 1. So there's an explanation of the half adder. Full adder is just two half adders together with receiving in a third bit, a third carry bit. And so, do I want to explain this here or here? I already actually have the explanation here. So this was the half adder, and this is the full adder. And that's the same thing I just did with the half adder, and this is doing it with the full adder. So the half adder receives in 2, and it outputs 2. So if we receive in 2 zeros, we output a 0, which would be in binary 0 here and a 0 here. If we receive in a 1 and a 0, which could either be 1 here, 0 here, or 0 here, 1 here, then we output a 1, which in binary is represented by a 1 here and a 0 here. That's why this is actually supposed to be the output, a 1 here and a 0 here. I didn't write the input side. If we input a 2 number 1, so this is a 1 and this is 1, the result will output a 0. The carry bit will output a 1. This is the same, but we have 3 values to input. So that's actually, I marked that at the bottom. So if we input all 3 of them are 0, then it's going to output a 0 for R and a 0 for C. If we input any one of these 3 as a 1, so we have a total of 1 over here that's coming in as a, I'll keep it with 1 instead of true, but coming on the inside we have one of the 3 is represented by a 1. Okay, it doesn't matter which, but just any of them are represented by a 1. Then the output will be R is 1, C is 0. And then finally, not finally, if we have 2, any combination of 2 of the 3 are coming in as a 1, then we output a 0 for R and a 1 for C. And now finally, if all 3 of them are coming in as a 1, then we output a 1 for R and a 1 for C. So there's the half adder and the full adder. And this is one example. So going back here, we show that we would need this is going to be a 6-bit adder, a 6-bit adder, a 6-bit adder, a 6-bit adder, 6-bit divider, 6-bit divider, 6-bit divider, 6-bit multiplier, and a 6-bit multiplier. That's what we would need to build this full circuit. Okay. I'm just going to show the details of one 3-bit adder. So again, this is what we would need, a 6-bit multiplier, 2 6-bit adders, and 2 6-bit dividers. Was that right? Whatever I showed in the first picture was right. I feel like that might not have been right. Because one of these was, yeah, it wasn't right because we just showed we need 4. Oops, these numbers aren't correct down here. Sorry about that. It was correct on the other slide. So now just to walk through this algorithm real quick like I did the other ones. Let's say if we want to add 2 numbers. So I didn't pick 2 numbers. Let's say that we want to add the numbers 1, 1, 0 and 1, 0, 1. Our output of this is 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is actually 2, which there's no 2 in binary world, so it's 0, carry the 1. So this is our solution. And to put this up here, we actually need to flip it because I have R0, which down here is on the right. Up here is actually on the left, so we need to flip it. So our answer should be 1, 1, 0, 1 as our answer. Our inputs, again, x0, this is the rightmost bit. So 0, 1, 1, 0, 1, 1. Then for y, we have 1, 0, 1, 1, 0, 1. And so if you set your inputs like I just did, imagine these are switches or something, and you're going to receive these outputs. You can imagine these are light bulbs, for example. And so walking through the logic, this is a 0, this is a 1. What do we have in our little chart here? I kind of made it so we have the total of 1 coming in. Total of 1 coming in is going to be 1 for R and 0 for C. 1 for R, 0 for C, which there's a line going from C1 to C1. I just didn't draw it to make it messy, but you can imagine this is connected. So we put this 1 goes to here. We bring in a 0 down here. So we have 0, y1, 0, x1, 1. So we're bringing in a total of 1. We go to this one. When we bring in 1, we output 1, 0. So 1, 0. Once again, this carries down. I just didn't draw it to try to make it a little less messy. So we output a 1. So this worked. This worked. So now on this side we have 0. y2 is 1. x2 is 1, so we have a total of 2 coming in, and this is a full adder. It has 3 inputs. So when we have 2 coming in, we output 0, 1. So 0, 1. 0 goes up to here, that checks out. 1 goes to here, that checks out. And so I think that's enough to show how the algorithm works for building for solving this problem using circuit design. Now you can, ideally I would really have liked to have made it out of the individual transistors, but as you can see from building it back up to the full picture, and knowing that what we just saw was only a smaller version of one of these sum blocks here. The multiply and divide blocks are actually even longer and more complicated than the sum block. So yeah, it's way too much. And then that's even given the fact that even at the block level, I showed adders. And at the adder level, they're made out of logic gates. It's not, and the logic gates are made out of the actual components. So you can see that it's very, but I wanted to think of it as designing the circuit from the components. It just was too daunting to actually display it that way. So yeah, that's everything. And I think there's if I were to say some final words, I would want to go back to here and just reiterate that, the whole point of the video is just to show some different ways that programming can look and feel at different layers of abstraction. And yeah, so that was my main point.